In this video, I am going to show you how to do integration using a technique called substitution. When you learned how to find derivatives, you learned the chain rule. The chain rule was used to find the derivative of a composite function that is a function inside another function. So an example of that would be something like x squared plus 2 raised to the third power. In this particular case, we have what I like to call the inside function, which is x squared plus 2. Now, usually that's called g of x. And then you have your outside function, which in this case would be this whole quantity being raised to the third power, so we could say x cubed. So the outside function is f of x, the inside function is g of x. When we create a composite function, f of g of x, what we do is we take the function f of x, we take out the variable x, and we put in x squared plus 2 in its place. So we have x squared plus 2 raised to the third power is a composite function. So if we look up here at this definition of substitution with indefinite integrals, we can see that we have the integral of a composite function f of g of x. So that means there's an inside function and there's an outside function. So we use substitution to find the antiderivative of a composite function. So as I started saying before, when finding derivatives of a composite function, you use the chain rule. Well, to find the antiderivative of a composite function, we use substitution. So substitution is the antiderivative's counterpart to the chain rule for derivatives. So in this definition, we have to have a composite function, and then very, very important is that also in the integrand is you have to have this g prime of x. That is the derivative of the inside function g of x. So you're looking for a composite function, and then you're looking for what is the inside function, and do we have the derivative of that inside function as a part of the integrand. And so to explain how we actually go about doing that, I will do by doing this example. So let's get rid of all this. And let's do an example here. Okay, the first example is 5x plus 4 squared. So first of all, why would we use substitution here? Well, we could just take 5x plus 4 and expand it. 5x plus 4 times 5x plus 4, and then find the antiderivative term by term simply using the power rule for antiderivatives. But we don't want to do that here. We want to use substitution. So I see that I have a composite function. The composite function is 5x plus 4 raised to the second power. The inside function, f of x, is 5x plus 4. Or I'm sorry, g of x. That would be g of x. The outside function is x squared. And so we have the composite function f of g of x. All right, so we have that. Then we ask ourselves, do we have the derivative of the inside function? Well, the derivative of 5x plus 4 is 5. Well, we don't have a 5, but we could introduce a 5 very easily. So I'm going to show you how to go about doing that step by step. So we recognize this as being a problem we can use substitution on. We have a composite function. I like to let u be equal to the inside function, 5x plus 4. And the reason I like to do that is because that's the way you're supposed to do it. All right, so the inside function, what we were calling g of x up here, we're going to let that be equal to u. Now what we want to do is we want to find the derivative of u. So du dx, the derivative of u with respect to x is simply 5. Then what I like to do, and there's different ways of doing this, and different instructors have slightly different techniques. The way that I like to do this is to solve this little equation for dx. So to do that, we would multiply both sides by dx, and they cancel out here. So we have du is equal to 5 dx, and then divide by 5. So we have dx is equal to du divided by 5. All right, so find the derivative of u and then solve that equation for dx. Now comes the substitution part. So what we're going to do here now is we are going to replace the 5x plus 4 with u. So we have u to the second power, and then we're going to replace dx with du over 5. This is why it's called u substitution. All right, so now what we have is we have an integrand which is in terms of u's. And so I like to bring the constants out in front. 5 is a constant. It's in the denominator, so it's 1 over 5 times the antiderivative of u squared du. And now we can simply use the power rule of antiderivatives. So we have 1/5 u cubed divided by 3 plus c, which then becomes 1/15. And we're never done with the substitution problem until we substitute the x's back in. So that's going to be 5x plus 4 raised to the third power. And that would be our solution. So that is the process of substitution. Let's just do a few more problems. Let's use red again. So first of all, let's look at this problem and say, do we have a composite function? And yes, it looks like I do. The inside function is x squared plus 3. The outside function is the quantity cubed. And so if we let u be equal to the inside function, the question is, do we have the derivative of this in the integrand? And yes, we do, because the derivative of u is 2x. So let's go ahead and find that derivative. Du dx is 2x, which is exactly what we've got there. Now, solving this for dx, just like I did in the previous problem, I'm going to not go through all those steps. We will end up with dx is equal to du over 2x. So we have our dx and we have our u. We can now substitute all of that stuff into our problem. So we have the integral of 2x. The x squared plus 3 is my u, raised to the third power, and taking out the dx and putting in du over 2x. Now, here's where the x's have to cancel out, and they do. That x cancels with that x. The 2's even cancel. It's not important if the constants cancel out. If they do, they do. And so we have the integral of u cubed du, and once again, we can now use the power rule for antiderivatives. So we have 1/4 u to the 4th plus c, which is 1/4 times x squared plus 3 to the 4th power plus c. And there is our solution. Now you could check either one of these problems to see if it's correct by simply taking the derivative of the problem. In fact, let's do that with this particular problem. If I take the derivative of this, I'm going to use a chain rule. So the 4 comes out times the 1/4 x squared plus 3 to the n minus 1 power times the derivative of what's in the parentheses would be 2x. These all cancel, and so what we have is 2x times x squared plus 3 cubed, which is what we started with. Voila, it worked. So the substitution is finding the antiderivative, And then if we take the derivative of the antiderivative, we should have what we started with. Next problem is a trigonometric problem. And we have a composite function. Right here we have the sine squared x. That could be rewritten as the sine of x squared. So the inside function is sine of x. So I let u be equal to my inside function. And of course the derivative of that is cosine, and we have that right here. Remember, we need whatever the inside function is, we need the derivative of it in the integrand. So let's go ahead and find du dx. Du dx is equal to cosine of x, or dx is equal to du divided by cosine of x. Now that we have this, and we have our u, we can substitute them in here. So we have 5u squared cosine of x times taking out the dx and putting in du over cosine of x. Now, I will be a very happy camper if any term with an x cancels out. And what do you know? I am a happy camper because the cosine of x and the cosine of x do cancel out. And so we're left with bringing the 5 out in front. I always like to bring my constants out. U squared du. We're simply reduce this down to a nice little power rule problem. So we have 5 times u cubed over 3 plus c, which is 5/3 times the sine of x cubed plus c. And of course, you could write that as 5/3 sine cubed of x plus c. That's a little bit nicer way to write when it's a trigonometric function like that. All right, next up. So we have a composite function once again, where the inside function, let's use dark blue. The inside function is 5x cubed plus 4. So let's let that be equal to u. Now, we don't know if this is going to work yet, because we have to say, okay, what's the derivative of that? The derivative of that is 15x squared. Well, I have an x squared out here, but I don't have the 15. That's okay. Don't worry if you don't have the constants matched up, as long as the variables are there. So du dx is 15x squared. Solving this for dx, dx is du over 15x squared. So you can see now what's going to happen. We have, we have u squared, and then taking out the dx and putting in du over 15x squared. I said don't worry about the constants as long as the variables are there. The variables have to be able to cancel out. So I'm left with a 15 in the denominator, so that's 1 over 15 times the integral of u squared du. Again, power rule, 1/15 times u cubed over 3 plus c, or 1/45 times u is 5x cubed plus 4 raised to the 3rd power plus c. And there is our answer. One more problem for this video. So, looking at our integrand, it looks a little bit different because we have a square root. But remember, the square root function can be rewritten with a rational exponent as the 1/2 power. So I have an inside function, and I have the outside function is the quantity being raised to the 1/2 power. So letting u be equal to x cubed plus 3, the derivative of this is 3x squared, and we can see that we have a 2x squared here, so that's working out, right? Again, don't worry that the constants aren't the same as long as the variables of your derivative is out here. All right, so we have, well, I didn't solve for dx yet. So dx is equal to du divided by 3x squared. All right, so we have the integral of 2x squared times u to the 1/2 times du over 3x squared. And once again, I'll be a happy camper if the x's cancel out, which they do. So I can put the constants 2 over 3 out in front times u to the 1/2 du. Simple little power rule problem. So we have 2/3. U to the 1/2 plus 1 would be 3/2 divided by 3/2 or times 2/3. Or in other words, 4/9 times my u, which is x cubed plus 3, raised to the 3/2 power plus c. And there we have it. All right, that's all I'm going to do for this video. I like to keep my videos somewhere around 15 minutes long because otherwise people fall asleep and get bored. So I'm going to do 5 more problems of substitution in my video, my class notes video on substitution part 2. And there'll be a little bit different types of problems, a little more complicated problems in some cases. All right, hope you enjoyed this video.